This is lecture 6, part 2, and I'm just briefly going to describe the cathode ray tube and one of its applications, namely that of the oscilloscope. In the lab component of this course, probably lab number 2, I'll go through the actual operation and use of the oscilloscope, but I just want to give you the underlying theory or mechanism behind the operation in this lecture part. In part 1, I described a tube that looks something like this, namely a discharge tube with the anode moved off axis so that the beam strikes the glass wall that's been coated with a fluorescent material, usually zinc sulfide, so that the particles, when they strike the screen, illuminate it. So the experiments that were described in the previous part indicated that the beam is actually composed of particles, negatively charged, and the electrons based on the charge to mass ratio. We can move the beam in the electric or magnetic field and that way get information. I somewhat oversimplified the picture in the previous part to get the focused beam, namely the spot on the screen. You need to have what's called an electron gun. So the anode is actually modified as a tube and actually a series of electrodes that keep the electrons from spraying, essentially. So you get a focused beam as opposed to a penumbra, is what they call it. So now that we have the electron gun and we have the means to focus the beam, we can insert the plates for imposing an electric field in the vertical direction. And we can insert a second pair of plates to set up an electric field in the horizontal direction. What one now does to control the spot, so to speak, is apply a sawtooth wave ranging from a negative voltage to a positive voltage. As the voltage passes through zero, the spot is dead center in the fluorescent screen as indicated. So negative pulls the spot to the left, positive pulls the spot to the right. And you apply the voltage sweep in a cyclical manner as indicated in the upper right so that you can make the spot move from left to right in a repeating pattern. So one applies the voltage as a sawtooth wave between the horizontal electrodes in the fashion indicated. So the result is that you get a sweeping pattern with the time base, namely the time duration of the sweep, set by the slope of the waveform. Naturally, if you increase the slope, go to much higher rates, you can get a faster sweep. And so, for example, if you had a waveform at 1,000 cycles per second or 1 kilohertz, the duration of the sweep across the screen would be 1 millisecond. And so you could see in real time the events, transient events on the oscilloscope screen. In the old days, you would have a camera on the screen. You could actually record these things going up to 1 gigahertz in duration. Naturally, as the rate goes very fast, the sweep appears as a fixed line across the screen because your eye can't perceive the spot. So now if you applied a 5-volt voltage, say, just a positive voltage across the vertical electrodes, the position of the sweep would shift upward from the middle of the screen. Similarly, if you apply a negative voltage, you would bring the trace, the spot movement, down below the middle of the screen. And so in this manner, you actually have the cathode ray tube behaving as a voltmeter based on a graphical interpretation and a calibration of the screen. Television, works in a rastering fashion. In other words, the voltages change and move the position of the screen, so that by changing the intensity of the spot in sort of an XY pattern, you create the image on the screen. If you now have a time domain signal, an AC signal applied to the vertical electrode, the vertical electrodes, you would see essentially a sine wave type fashion if it happened to be a sine wave. So you would see the pattern repeating on the screen, and in this case you would be able to record the signal, the AC signal, and determine its parameters in the time domain, namely the frequency. And if you had transient events, you'd be able to detect them in real time. Again, if you got the signal going very fast, you would see a static sine wave or whatever the waveform happens to be. And so here is an example in which the cathode ray tube would be used as a detector for a transient type of experiment or transient response in a chemical system. So the layout is this. I have a tube containing a sample. It can be gas, liquid, it can be anything you want, any type of sample, as long as it'll transmit light. On the left-hand side, we have a light source that's continuous, and the wavelength is selected by a monochromator there, indicated by the reddish box. Above and below the sample tube is our flash tube, similar to the electronic flashes you find in photography. And then the photomultiplier tube is the detector. So we talked about photomultiplier tubes in previous lectures. And the photomultiplier tube is connected to usually an amplifier system and other circuitry, but ultimately the observation point is the oscilloscope screen. So what will happen is the tubes will flash and they will promote the sample to some excited state, and the wavelength in the continuous beam source is connected with the excited state, so you'll be able to see it as a result. And for the limited time that the excited state exists, you would see the transient, namely the formation of the excited state indicated by the rapid rise on the oscilloscope trace, and then the decay, usually exponential or bi-exponential, back to the ground state. So from the oscilloscope's capturing of the changes in the absorption spectrum of the system, you can get an idea of the population of the system, namely how much of the excited state is produced, and the kinetics of the decay, the rate of decay, and its return to the ground state. So these are very fast, responses, obviously, and they need an oscilloscope. The early magnetic resonance experiments work almost directly this way. You would actually see the spins moving in real time. We'll talk about this after we get through mass spec. But you can also scan the monochromator on the left now. And from the magnitude of the straight vertical piece on the oscilloscope trace, you would be able to record the variation of that with wavelength and actually determine the absorption spectrum of the excited state species. So in conclusion, we have shown that the cathode ray tube is essentially a visual or a graphic voltmeter. The position of the spot on the fluorescent screen is an indication of the voltage at any given time, with time being the x-axis. There are ways to set up the the oscilloscope to actually do XY plotting, so you can plot voltages versus current and so on. We'll do that in the lab. So you can actually make an XY plotter on the screen, and this is essentially how television works, or the old televisions used to work. The advantage of the cathode ray tube and its more modern versions are that you can see voltage changes in real time and in very short time. So you can observe changes in transients and waveforms that you could otherwise not see or measure on a conventional digital voltmeter, because the response time on a digital voltmeter is too slow. You can't read out the numbers anyway as they go by. So that's the motivation. The electron tubes are considered obsolete. They have certain advantages. They're more robust. They're more they're not as sensitive to temperature, so that in high temperature situations or in high voltage applications, they are actually preferred, so they're still made. But most simple instruments now work with solid state materials. So the LED devices that you find on, for example, your computer screens now, which are very flat. The old computer screens were cathode ray tubes. And at the bottom of this particular slide, I've got some bibliographic references.